Linux isn't very friendly to newcomers. An opinion which I shared on Twitter a while ago and was of course received with some relatively mild backlash from a couple of true fanboys. I do stand by this position still, but with this video I'd like to show you that regardless of that fact, if you spend some time understanding how it all fits together, when it comes to Linux that is, then maybe, just maybe, it can become a little less intimidating. Okay, before we start, since the majority of this video will be spent, well, in Linux shell, I figured it made sense to prepare a written tutorial to go along with it so that you can have a copy-pastable version that you can come back to and, well, just copy and paste stuff if you want to follow along at your own pace. Second, I've set up a really basic Gitbook repository which at the moment has nothing else in it except, well, for this tutorial. That being said, think of it as a documentation starting point for the whole router project going forward, so I'll gradually add not just stuff from my YouTube videos, but also all the documentation for the device. The GitHub repo on which it is based off is not yet public, simply because I need to experiment with it a bit to figure out the best way to organize it, so that once we do make it public, it will be ready not only for, let's say, a positive reading experience, but will also encourage all of you to contribute, be it with correcting our mistakes, suggesting more or better content, or simply writing articles/tutorials yourself. Third, because I'm working on an M1 Max Studio, which is ARM64 architecture, I don't need to cross-compile for our board that I'm working on, because it is also ARM64. Since I know not everyone is using this kind of setup, I'll provide you with a link to a PDF that runs you through on how to set up cross-compile tools on your x86 machine. It only takes a couple of minutes to set it up and then use exactly the same commands that I do, because they'll automatically leverage those cross-compilation tools. And fourth, we'll spend the majority of this tutorial in 3 directories, so it makes sense to make all of them ahead of time. I already created a directory called YouTube for the part 1 video, so I'll use that one, but feel free to name it however you want. I'll refer to this directory as our base directory throughout the video. The second directory that we'll also need is one that's created by the TFTP server software, which you have to set up on your own. But it really just takes a couple of minutes, and in my case, it also created an /srv/tftp directory. Inside, I also created a directory called YouTube, primarily to keep things a bit more organized. Which brings me to the last directory, and that is /mnt/SD card. Towards the second half of the video, we'll start building an SD card image, and it's this directory where we will copy all the necessary files into. If you remember from the previous video, a link up here if you haven't seen it yet, for Linux to boot on an embedded device, we need 3 key components. The kernel, which is the brain of the system, a root file system, which is where all the files reside, and finally the device tree that tells kernel how all the hardware fits together. I won't go more into details at this point because we will build each of those throughout the video, and by the end you'll hopefully have a better understanding of all of them. The first thing we'll do is download and build the kernel. If you've never done it before, don't worry, it's actually pretty easy. I mean, optimizing it can become an art in itself, but if you stick with the defaults, then it literally takes 4 commands, or 2 really, if we ignore the downloading and uncompressing steps. Speaking of which, let's do exactly that. For the purpose of this video, I'll use the official kernel, which you can find at kernel.org, and as you can see here, there are several versions, the oldest one of which was first released all the way back at 2018. I'll use the latest long-term version, which as of recording of this video is 6.6.51, so let's right-click on the tarball, copy the link address, then download it into our base directory by entering wget and pasting the link in. Depending on your internet connection, this might take a while because the file comes at a whopping 200 megabytes, so if you need a toilet break, now is the time. Once it's done downloading, let's uncompress it and move into the kernel directory that we just created. Here, you can make it as complicated or as easy as you want. If you want to take the easy route, the only thing you need to do is enter make dev config, which will read the contents of the file, path to which I'll show you on screen. but I will not take the easy way, and there's a reason for that. Two, in fact. See, I don't want to use the default configuration, at least not the one that this kernel provides. Instead, what I'll do is use the one that the vendor for my board, so NXP, provides on their GitHub repository. So I'll go into that repository, navigate to their devconfig file, and simply copy it into arch/arm64/configs there in our kernel tree, where all the other configuration files are already stored. I'll name it nxp_devconfig because it makes sense, but I could name it pretty much anything I want. Now, instead of make devconfig, I'll enter make nxp_devconfig, the result of which will be this .config file. But we're not quite done yet, because as it is, if we build the kernel now, it will take approximately 41 megabytes of space when uncompressed. I mean, it's not the end of the world, but it can be trimmed down significantly by simply entering make menu config, then going into platform support and unselecting all the platforms that we don't need to support. In my case, I'm using a Layerscape CPU, so that's the only thing I'll keep checked in here. This change alone reduces final kernel image size from 41 megabytes to 24 megabytes, which is more than a 40% reduction. A win in my book. And since we're talking about size reduction, you could also go the other way and use something called a tiny config. So make tiny config, which will build the smallest kernel image possible, weighing only at around 1.8 megabytes. However, in that case, you would need to go into menu config and add all the things yourself, which honestly is a very cumbersome and time-consuming process, so I don't really think the reduction in size is worth it, especially given that most devices aren't that constrained when it comes to storage. Okay, now we have everything in place to build the kernel, which we do simply by entering make -J8, and depending on the amount of features you added and the resources of the machine that you're building it on, this step might take anywhere from mere minutes to an hour or maybe even longer. The result of this are files that could be put into two categories. The kernel itself, which comes both in a compressed and uncompressed variant, and modules, which are files that kernel doesn't use at the time of booting, but can be plugged in, so to speak, when the kernel is already up and running, that is. One more thing worth mentioning here before we move on are also the device trees. We went over them in the previous video, so the only thing you need to know in the context of building the kernel is the fact that because we added support for our board, it also built the relevant device trees automatically. Our board comes with 6 of them, I think, and all of them can be found in this DTS directory. The next step we need to do is build an initial RAM file system, also referred to as initramfs. Now yes, this is an optional step, but I figured I'd include it in this video anyway, because well, initial RAM file system is a very useful part of booting Linux, as you'll hopefully learn throughout this section. Now, unlike our final Debian root file system, we will aim to build something much smaller here, and the tool that is perfect for this is called BusyBox, and its main superpower is that it can pretty much build the whole Linux file system around one single file, no bigger than a few megabytes. And don't worry if it sounds confusing, you'll see what I mean in a second, but in order to get there, let's download the latest version, which as of recording of this video is 1.36.0. So let's go to the GitHub repo, click on the tarball, save the link address, and finally download and uncompress it into the same base directory. And also, just like with the kernel, we'll go into menu config by entering make menu config and change a single setting, which is in settings, and it says build static binary. This is all we have to do, but feel free to browse around to check what's on the menu, so to speak. And if you like anything you think will be useful, just add it by pressing Y or spacebar when focused on the option. Since I don't need anything, I'll exit the menu config, which will automatically ask me whether I want to save the new configuration, to which I'll answer yes. Of course, just like we did with the kernel, we now have to compile it and use the same make -j8 command that we used earlier. Again, depending on your PC, this might take a while, but luckily nowhere near as long as with the kernel. And once it's done, we also need to run an additional command, and that is make install. This will, as the name suggests, make a directory called _install, into which it will put a single file and a bunch of symbolic links, all pointing to that same file called, unsurprisingly, BusyBox. And you know how big this BusyBox binary is? Just a little more than 2 megabytes. And guess what? Once we compress it, it's gonna get even smaller than that. But first, we also need to add 2 key ingredients. A proper directory structure that Linux expects, and B, an init file. To do that, let's go back to our base directory and make a new one called initramfs, then create all the necessary directories within it, and finally copy all the symbolic links and the BusyBox binary into this new directory. I won't go through each and every directory we just created, but if you have any experience with Linux, then you'll recognize most of them immediately. What we will spend a little more time on though is the init file. You see, kernel, when booting into this initial RAM file system, expects an executable file called init at the very root of the file system, and it's this file it will call once it's done booting, and if this file is missing, you will get what's known as kernel panic. So to avoid that, we'll make the init file next, and I'll be using a cat command, but you're of course free to just use a normal text editor. As long as it's placed in the root of the file system and has the executable flag on it, we're good. And if we ignore this ASCII art text, it doesn't really have to include much. We mount both proc and sys virtual file systems so that BusyBox can access either. Then we show this funky graphic with the info about kernel booting time, and finally we execute a shell giving us control of the system. Now that we have the file in place, we run the chmod +x on it to make it executable, and our initial RAM file system is ready. Well, almost. The only thing left for us to do now is to compress it, because Linux expects it to be a single file that is called a CPIO archive. So let's change the directory into initramfs and run this command. I won't go into each part here because there's plenty of documentation on how to make a CPIO archive, and the result of this command is exactly that. If we go back to our base directory now and list what's in it, we now have an additional file that's pretty much half of what the initial BusyBox binary was in terms of size. In my case, it's just a little over a megabyte. The last thing we need to do then, if we plan to run it from U-boot, is also to convert it into a format that it understands. So we'll just run this mkimage command so that we basically end up with 2 RAM file systems. I'm sure U-boot can be configured to also understand the original one, but to be completely honest with you, I didn't bother to check because it literally takes this one additional command to convert it into a format that it does. Now that we have everything ready, so 1. Kernel that we built in the first step, 2. Device trees that were also built alongside with the kernel, and 3. The initial RAM file system, let's copy all of them to our TFTP server directory that I prepared for this tutorial. First, we'll copy the kernel, both its compressed and uncompressed version, because why not? Then we will copy all the device trees for our board, and finally the 2 CPIO files we just worked on. Okay, time to generate the fit image, which essentially just merges all 3 together. So what I'll do next is change directory to the TFTP server/YouTube. You can see that all the files are here, so it's time to make what I call a recipe file for the fit image, that is. It's a fairly simple file. Basically, we define the 3 major components, so kernel, device tree, and the initramfs file, and merge them all together. But it's not the merging itself that I think is the strongest part of this file. It's the fact that I could have listed multiples of any of the 3 components and then just write additional configurations down in the bottom using any number of different combinations. Which means that yes, I could have several kernels or device trees all combined into a single file. Now that we have our recipe in place, let's again run the mkimage command that we've already used before. We'll just pass the -f parameter to our its file and tell it the name of what our output file should be. There we go, the moment of truth. I'll now switch the screen to our development board, turn it on, which will get us into U-boot, and run the commands necessary to boot this fit image. But before we do that, just a quick reminder. I go much more in depth in regards to U-boot in the part 1 video, so if you're not sure what you're looking at here, I urge you to check it out. Anyway, there's very little we have to do here since U-boot is already connected to my network. All I need to do is fetch the board.itb file, save it into memory, and run the bootem command while giving it the same memory address we just stored it at. Time to run it? Not quite, as I also need to make sure that one last thing is in order, and that's an environment variable called bootargs. You see, kernel, when being booted, can be passed a huge number of parameters to behave a certain way, but for us, the most important one at this moment is called root. It tells the kernel what device to look into for the root file system, and in this context, RAM is considered a device as well. So what I'm gonna do here is make sure that the root parameter is set to /dev/ram0. And while we're talking about kernel parameters, let's also add two more, one called root weight and the other called RW. Root weight isn't as important right now, and we'll talk about it a little bit later, and RW isn't either, but if we don't set it, then the file system will be mounted as read-only, basically preventing you to write any files. So yes, RW stands for read-write. I mean, for the initial RAM file system, it doesn't matter as much because even if you do write to it, it's gonna get discarded after you reboot the device, but I think it's worth mentioning here nonetheless. Okay, now is the moment of truth. If we did everything correctly, then the kernel should boot in about 5 to 10 seconds and our funky ASCII art should appear along with the shell that we configured it to launch. Without going too much into details, mainly because it's out of scope for this video, many embedded devices use this environment to mount and boot a squash image. SquashFS, in case you don't know, is a highly compressed file system which is perfect for many embedded devices that come with very constrained resources. But since we don't have that limitation, let's go ahead and build ourselves a fully fledged Debian system. This episode is brought to you by PCBWay. I've been working with them on my custom keyboard project and I was super impressed with their speed, quality and price, so I'm more than happy to recommend them to anyone who needs any kind of PCB manufacturing done, whether it's just for a couple of prototypes or if you need a larger production run. Link to their website, of course, down in the description. Back to the video. I'm now back on my development machine inside the base directory, and the first thing I'll do is create an empty SD card image using a utility called QEMU-IMG. There are many ways to do this. I just prefer this way because not only is it a single command, but it's also fairly easy to understand. I'll give it 4 GB, even though the SD card I'll use later on has 256 GB of capacity, and that's because there's no need to give it more at this stage, since I'll also have to flash the SD card with it, and 265 GB would simply take forever. Instead, we can resize it from within the initial RAM file system on the device itself. See, I told you it can be useful. Anyway, now that we have our image file, it's time to make the 2 partitions that we'll need. One for our kernel, device tree and RAM file system, and the other for our Debian root file system. We don't need anywhere near 500 MB for the kernel, but it's a good idea to give it some more space in case we want to upgrade to a newer version down the line, while also keeping the old ones. The keen-eyed among you probably also noticed we're not starting at 0, but at 1 MB. That's because GUID partition table, as it is called, also needs to be somewhere, and by default it's at the very beginning of the drive, or in our case, our image. Now that we have our image created and partitioned, it's still only just a file, so I'll run this low setup command to turn it into a loopback device a fake drive, if you will. For this and all the following commands for that matter, I need to use sudo because we're working on devices and Linux isn't too keen on giving everyone that kind of permissions. With our loopback device in place, I'll then run the kpartx command, which then attaches these partitions and maps them to /dev mapper loop 0p1 and /dev /mapper /loop 0p2. Whew. And now that they are attached, we can also turn them into proper file systems by passing each to the mkfs.ext4 command, which makes them ready to be mounted so that we can finally start copying files into them. Because we have two partitions, we'll also create a boot directory in it and then first mount the root file system partition, which is partition 2, and then the boot partition, which is partition 1. Obviously, since we didn't copy anything over yet, they are empty. But if we actually check both of them, we can find a directory in both called lost plus found, which is an artifact of ext4 file system and an indicator that all the commands so far have worked properly. And because they did, we can now finally install Debian into the second partition, and here I will cheat a little. You see, Debian already provides a tool called deb-bootstrap, which pretty much takes away all the complexities of building a file system yourself, because, let's be honest, that would take far too long and, more importantly, would be prone to errors and plenty of frustration. I mean, feel free to do it yourself. I'll even link to a great resource for that called Linux from Scratch. But I just prefer to do it the easy way because it's reliable and, just as important, repeatable. And in fact, it only takes a couple of commands. The first of which, obviously, is to bootstrap Debian into our mounted partition using two extra parameters. So the architecture we're using on the target system, which in my case is ARM64, and the version of Linux, or Debian Linux that is, that we want to use. And since the latest one is called Bookworm, let's use that. There we go, the files are now copied over, but there's also a second stage we need to run if we're building for a foreign architecture, which in most cases we do. For that, we have to use the change root command, which in a nutshell changes the root file system to whichever we give it to as a parameter, and also executes the command we call, in our case bash, in the context of this new root file system. In the context of this new root file system. Here, let's execute deb-bootstrap with the second stage parameter, and once it's done, our file system setup is pretty much complete. But before we leave this environment, let's also do some important housekeeping. First, let's install all the packages that we'll initially need for the system to run, the most important of which are networking, so that, you know, we can actually get online. Time management, because if the system doesn't have proper time set, then some services won't work properly. And finally, udev, which, among other things, makes sure that the terminal that we use is correctly configured. Obviously, we can install pretty much anything we want here. Just keep in mind that we only have 3.5 gigabytes of storage available at this point. And finally, we also need to set a root password, because if we don't, we will not be able to log in when the system boots, since Debian doesn't allow passwordless login by default. All set, we can now type exit to get back to our base file system, where we need to take care of the last bit, and that is the boot partition, which is still empty. Let's change the directory to the kernel that we've built at the very beginning of the video, and first run make install while also giving it the path to the boot partition as the environment variable. This part is actually very important, because if we omit it, then kernel will be installed on the boot partition of the system I'm working on, and well, I don't want that. Next, we will also install all the modules that were built along with the kernel by entering make modules install and giving it the root file system as the location. This is because Linux expects them to be in the /lib/modules directory and not on the boot partition where the kernel is. And finally, let's also make a DTB directory on the boot partition and copy over all the device trees that we might need. By the way, I should point out that this complete boot partition is optional and our system will work perfectly fine without it. In fact, we could just flash the fit image we built earlier onto a NOR flash chip and always use that to boot into Linux. But boot partition with everything needed in order to, well, boot the system successfully is generally a good idea in case you need to upgrade the kernel down the line and also have an option to roll back if that's unsuccessful. And with that, we have everything in place to flash the SD card. But before we do that, some cleaning up is in order. Let's unmount both partitions, so loop 0p1 and loop 0p2, then detach the loopback device from the partition mapper and finally destroy the device entirely. And don't worry, our data is safe, happily sitting within the SD card image file, which we can now finally flash our SD card with, or a USB drive for that matter, because it will work just as fine. For this purpose, flashing that is, I recommend a tool called Balena Etcher, and I'll leave a link to it down in the description. I flashed my SD card off camera because there's no point in you watching me do that. I booted into U-boot and will now boot into our newly set up Debian file system. Well, at least I'll try to, and I hope it works. This time around, we'll skip initial RAM file system completely, but what we do need to make sure is that the root boot argument is now correctly pointing to the eMMC device rather than RAM. And remember that I promised I'll also explain the root wait argument? Well, here's where it becomes important. You see, kernel, when booting, also initializes all the devices that it wants to work with, and our eMMC device is one of them. But the process of the initialization can sometimes take longer than the kernel needs to fully boot, which means it'll panic if it's done booting but the device into which it looks for the root file system isn't ready yet. And here's where the root wait argument comes in. It instructs kernel to pause in a way and wait for the device with the root file system to be fully ready and only continue once it is. Also, pay attention to how I'm no longer loading the files using the tftp command. This is because we don't need to fetch them from our TFTP server, because everything that we need is already loaded on the boot partition of the SD card, so we're instead using the load mmc command. Okay, let's now boot into Linux. There we go, everything seems to be in order, so let's scroll back a little bit to this point. See how here the output look changed somewhat with these green OK marks? This is where kernel is pretty much done booting and is then passing the torch to the Debian's init system called systemd. Just like with our initial RAM file system earlier, it needs to call a script in a particular location that acts as the primary program with the process ID or PID of 1. This is the master process, so to speak, and all other processes that it spawns are children to this process. We can also verify this by running the ps command in Linux and see that indeed it's the /sbin/init that was called first by the kernel, and it does indeed have the PID of 1. So now that we have our Linux up and running, there's also one final piece of the puzzle that we need to put into place, and that's the boot partition. If we check the boot directory, you'll notice that it's empty, and that's because we haven't told Linux to automatically mount it at boot. We'll do this by first listing all the partition by their UUID, then adding said UUID of our first partition into /etc/fstab file along with some configuration. I won't go into details here, suffice it to say, we're mounting the partition 1, which has this UUID under /boot, and it is of the ext4 file system. Once I save and exit the file, all I have to do next is run mount A, which will automatically read this file and mount the boot partition not only now, but also automatically at every boot going forward. And just to be sure it's actually working, let's now try listing the boot directory, which, as you can see, now has all the files we've put into earlier. There we go, everything seems to be in order, so time for a little recap, for which we'll go into a bit more of a helicopter view. When the CPU boots up, it runs the bootloader 1 code that's built into its internal ROM and is primarily responsible for turning on the pins that it expects will have storage medium with bootloader 2 code on it, then runs that. Bootloader 2 is responsible for RAM initialization, and once it's done, it calls bootloader 3, which holds our U-boot. Here, we need to fetch at least the kernel and a device tree, but also optionally the initial RAM file system, save all three into RAM, and then start the kernel with correct boot arguments. Once the kernel is done booting, and if we included the initial RAM file system in the boot command, then it will call its init script at the root of the tree, or if we didn't, it will call /sbin/init on whichever device we've set the root boot argument to. And if the latter is the case, then this init file is provided by the Linux distribution, in our case Debian, which then takes care of running all the other processes that our system also needs to work properly. Easy! Tomasz from Slovenia, signing out.